I'd like to work through a full example of assessing an experiment while following uncertainties through that experiment to see how it works, to see how this whole process works in detail, because I've done some examples of individual calculations using uncertainties, following uncertainties through the calculations, but I want to show you how that works in a whole experiment. So here's a set of data collected in an experiment where we have these two masses coming together and colliding and sticking together and moving away as a single total mass. This could be two asteroids in space colliding. It could be two carts in a lab colliding. The one thing we're going to assume is this is all moving along a straight line and they're hitting straight on, so it's all in one dimension of motion. So I'm kind of ignoring vectors here just for simplicity for the moment. So, okay, we took some data. We're imagining we've taken some data that the mass of the first object is 800 grams, the mass of the second object is 300 grams. Each mass is uncertain by plus or minus 10 grams. That was that's our uncertainty in mass is the same. Maybe that's the precision of our balance we use to measure them or something. We measured the initial velocity, well, x component of velocity, I guess, of the first one to be 2.8 meters per second with an uncertainty of 0.1 meters per second. And the second one is moving in the other direction, which we'll call the negative direction, the negative x direction. And we measure that with a speed of, I guess its velocity is negative 4.7 meters per second, plus or minus 0.3 meters per second. Maybe it was a little harder because it was moving faster, harder to get that measurement precise. And finally, after the two glom together, at that point, the total object is moving this way, and the measured final velocity was 0.90 meters per second. And again, moving slower, we were down to that 0.10 meters per second uncertainty. So this is the data we've collected. And the question we want to answer is momentum conserved in this collision? Now, as you know, momentum is a vector, and it's the quantity of motion of an object. It's a vector quantity. Again, we're just paying attention to the x component, and for simplicity of writing for this one example, I'm not writing the x subscripts for all the x components. I'm just writing down v1 and v2 and things, but assume this is all x component stuff. Okay, that's my setup. That's the question. I want to know, is momentum conserved in this interaction? So, okay, that means I need to calculate a bunch of momenta to do this, right? I need to figure out, for example, the momentum, the initial momentum of mass 1. And we've done this calculation in a previous video. It's m1 times v1. And so multiplying those together, m1 times v1, 800 grams times 2.80 meters per second, gives me 2,240 gram meters per second. Maybe I should write it as 2.240 kilogram meters per second, but I've written grams here. I'll keep it consistent. So I've got that, and in a previous video I talked about this. This is the product of the mass and the velocity, the product of two quantities, and when we multiply two quantities together to do their uncertainty, we compare their relative errors. We can't compare the absolute errors because they have different units, so we compare the relative errors. And for this video, for simplicity, I'm going to use the dominant error rule. You could use a more complicated professional error propagation like the adding uncertainties in quadrature, and that would be a much more precise way of doing it. We're going to use the dominant error rule just to keep things simple for now, but the process will be the same throughout. So it's a product. The dominant error rule says I compare these two relative uncertainties, and I just keep the bigger of the two. So my uncertainty in the product m1 times v1 is going to be plus or minus 3.6%. 3.6%. And if I multiply this 2,240 gram meters per second by 0.036, if I do that, I will find that this corresponds to plus or minus 80 gram meters per second. I think that's even exact, or at least I don't think that's rounded. So anyway, plus or minus 80, that's my momentum, initial momentum of object 1. By the same token, the initial momentum of object 2 is m2 times v2. And once again, that's a product of these two values. If I do the multiplication, multiply it out, I'll get negative 1,410 gram meters per second. And again, my dominant error rule will tell me that I look at this, and the 6.4% is a bigger uncertainty. So plus or minus 6.4%. And if I want to know what it gives me for an absolute uncertainty, I can just multiply 1410 by 6.4%. I take absolute values for uncertainty. Uncertainty is always positive. So my uncertainty, multiplying the absolute value 1410 times 6.4%, 0.064. When I put that together, I will get that this is equivalent to plus or minus 90 gram meters per second. Those are my uncertainties there. And I guess I may as well, since I'm doing this, I may as well, I got these first two, P1 and P2, I can ask what is the total momentum initially. So P total initial is just P1 plus P2. Wow, it's making me feel creepy not writing vector signs on top of all of this. Again, just for this example, P1 plus P2. When I put it together, when I add those up, I will find that I get 830 gram meters per second. Hope that's right. I'm doing this 2240 minus 1410. That gives me the 30. 22 minus 14 is 8. So yeah, this is right. 830 gram meters per second. I'm checking my notes over there as I go, which is so I don't have to do a calculator all the time here. And when I add and subtract, again, my rule when I add and subtract is here I have the same units for P1 and P2. I don't compare the relative errors. I compare the absolute uncertainties, not the relative uncertainties. So here, looking at those, well, the 90 is a bit bigger than the 80. So this is plus or minus 90 gram meters per second. If I wanted to, I could then use that to figure out my relative uncertainty. That's the same as plus or minus 11%, if I wanted to work that out. So I can find that, but my initial total momentum is 830 gram meters per second plus or minus 90 gram meters per second. That's my calculation, and you can see how I used my uncertainty rules each time. The product rule here compared relative uncertainties, product rule here compared relative uncertainties, sum rule here compared absolute uncertainties. And I got my result for my initial total momentum. Then I can shift gears and I can say, what is my final momentum after they've combined together? Well, to do the final momentum, I need to know total mass. I guess P final is going to be mass total times V final. That's what that is. And so I need to know what my total mass is. M total, if I want to put it together, we did this calculation in an earlier video too. M total was 1100 grams. And in that earlier video, we just looked at these, did the dominant error rule and said, well, we just do plus or minus 10 grams. Again, that was an underestimate because it's an underestimate because these are very similar. Dominant error always underestimates, but underestimates most when the two uncertainties are similar. And so really it should be plus or minus 14, whatever. And if I want to know the relative error there, which I will, that relative error is about, so it's the same as plus or minus 0.9%, because this is about 10 out of 1,000, which would be 1%, and it's a bit less than that. So 0.9%. All right, that is my M total. So then my momentum final then is this total mass times V final down here, 0.90. And so I can put that together. I get that this is 990 gram meters per second. And then I need to work out what my uncertainty is. Well, it's a product, mass times velocity. And so my velocity final uncertainty, product means relative uncertainty is what I look at. 11% relative uncertainty here, less than 1% relative uncertainty there. I know which one's going to be dominant, plus or minus 11. And that plus or minus 11% is going to be exactly the same. It's going to come out to be the same as a plus or minus rounded to significant digits, I guess, it comes out to be plus or minus 110 gram meters per second. So there are my results. My initial momentum is 830 gram meters per second plus or minus 90 gram meters per second. My final momentum is 990 gram meters per second plus or minus 110 gram meters per second. And I want to know, are these consistent with each other? Is this, is momentum conserved? Was my question. How do I answer my question, is momentum conserved? Well, I mean, I look at this, oh, no, it is not. These are different numbers, right? 830 compared to 990, different numbers. Can't do anything about it, too late, we're out of luck. It's not that bad. It's not that bad. We actually can do something with this, because what we can do is, let me visualize this by drawing a number line. I should have planned ahead for how big of a number line to draw. I need to go up to about 1100 and down to about 700. Okay. So what I'm going to do is draw a number line and have like 700 here, 7, 8, 9, 10, 700, 800, 900, 1,000, 1,100, and so on. So there's my number line, and maybe I can even put a couple of little intermediate marks in here just so I can, my scale is off. Oh well. This is what happens when I eyeball things. But this is what you do, draw a sketch. And what I'm going to do, I'm going to put both my numbers on here. So my initial momentum is 830. That's going to be about here. P initial, P total initial is there at about 830, and plus or minus 90. So, well, 830 minus 90 would be 740, about here. And 830 plus 90 would be 920, about here. So somewhere in this range, that is my uncertainty range for my initial total momentum. Then I can do the same thing looking at my final momentum. P final is 990. 990 is all the way over here. That's outside of this range. So you might say that's bad, right? I'm out of luck. 990 is about there, but plus or minus 110. 990 plus 110 would be 1100 out to about here. And minus 110 would be 880. That's going to be about here. So if I put those together, this is my P final point. And so if those uncertainties, the uncertainty initial and the P initial and P final, neither one is inside the other one's uncertainty range. They're both outside of each other's uncertainty range. But you'll notice the uncertainties overlap in there. And as long as those two uncertainty ranges overlap, that means that you have not ruled out the possibility that these two values are consistent. If the true initial momentum had been 900 and the true final momentum had been 900, that would be consistent with both of these stated uncertainties. And so there is room for momentum conservation to be verified by this experiment. So this tells me that my experiment is consistent with momentum being conserved in the process that we took these measurements for. That's kind of how you do this. Now, I will say there are that this is one way of visualizing this. There are a lot of subtleties about this that I haven't talked about here. For example, I don't know how much I want to go into. One subtlety is that people sometimes mean different things by uncertainties. If you're talking about an uncertainty that means I am like 95% sure that it's somewhere in this range, that the true value is within 10 grams of 800 grams, and 95% sure, then the reasoning I've talked about is exactly what you want to think about. On the other hand, there are some very common ways of calculating uncertainties in which you say, I think that my uncertainty, the plus or minus 10 grams, it's almost certainly within 10 grams of this, but it might be within 20 grams one or the other. That's less likely, but still might happen sometimes. like 95% certain it's within 20 grams, but within 10 grams, I'm pretty sure, I'm almost certain it's within 10 grams. I'm pretty sure it's at 10 grams, 95% sure it's within 20. Some people think about uncertainty that way. And in that case, you might say, oh, well, then really I could double each one of these. If this was it's probably right around here, but it could be twice as much. If that was the way we interpreted it, then you might even double these sizes of these ranges and get them overlapping even more. On some level, if you have to know what you're using, how you're thinking about uncertainty. But from this picture, if this range is your 95% certain range on both of them, then you're looking for, do they overlap? That's kind of what you're looking for. That's maybe the best way to visualize all this. One other thing you could do if you wanted to, instead of looking for overlapping ranges, one way of saying is momentum conserved is to say you could also ask, is the final momentum minus the initial momentum equal to 0? That's an equivalent thing to saying, is momentum conserved? Are these equal? Is the same as, is the difference equal to 0? And there we could just take a difference, right? We could do P final minus P initial. We know how to do that. P final minus P initial is equal to 990 minus 830 is going to be 160 gram meters per second. And then what do? Well, that's a difference. We're subtracting two things. In sums and differences, we compare the absolute uncertainties. And then if we're using the dominant error approximation, we pick the bigger of the two, 110. So plus or minus 110 gram meters per second would be my dominant error rule doing this. And at that point, you say, oh, 160 is different than 0, and it's not within 110 of 0. So you might say, oh, maybe thinking about it this way, maybe it's not within our uncertainty. But the two things to say there are, first of all, if you assume this 110 is just the probably in this range, but it could be twice as much out, and I wouldn't be too surprised, like 95% is twice as much out, then that would mean the 110 would double the 220, and this is definitely within two uncertainties of 0. And so that's a way of saying, yeah, it's reliable. On the other hand, also, if I had not used the dominant error approximation, but if instead I had done a more professional uncertainty analysis and had added these two in quadrature, because 90 and 110 are pretty similar, to do a more professional error propagation there, you would find, let's see, 110 squared plus 90 squared equals, and take the square root, 142. So if I had done a more professional thing, it would have been plus or minus 142, and that's even closer to 160. At that point, you might say, yeah, maybe this is good enough. Honestly, if I had been using professional error propagation all along, this 10 and 10 would have been a 14, and that might have actually increased it. This would have been a 14. It would have been, well, no, that wouldn't have changed it. That's the smaller error. I don't know. The point is, it's pretty close. It's not too far off, even with just one uncertainty range. And if you're using uncertainty in a way where you double it to be sure, then this is certainly within two uncertainty ranges of 0. And so again, I'd say, yeah, momentum seems to be consistent with being conserved in this experiment. So there you go. That's how you can go through and look at the results of an experiment and decide, even though these numbers are different, are they so different that I should worry, or are they close enough that it's probably reliable? And this shows you how you can use uncertainty calculations to know, yeah, this is close enough to be reliable. This is how I know how much I can trust these numbers, and this is what it means.